Good evening, everyone, and welcome to another session of IITD JHU's Smart Seminar Series. Today, we are pleased to host Mr. Dibakar Roy Sarkar, a PhD candidate in the Department of Civil and Systems Engineering at Johns Hopkins University. So, just to give you a little bit of background about Dibakar, he has completed his master's degree at IIT Madras, where he was awarded the Tata Motors Excellence Scholarship for his academic distinction. Prior to that, he earned his bachelor's degree from the Central Institute of Technology, Kokrajhar. At Johns Hopkins, he received the Creel Family Engineering Fellowship in the first year of his PhD for his strong potential for high impact research. His work spans computational mechanics, scientific machine learning, and PDE based control, with a particular focus on developing physics consistent and data efficient AI frameworks for complex engineering systems. So, building on this diverse foundation, today Dibakar will be presenting his recent advances in operator learning for physics discovery and inverse modeling in his talk that is titled as Learning Hidden Physics and System Parameters with Deep Operator Networks. So, with that, please join me in welcoming Dibakar. We look forward to your engaging and insightful presentation. Over to you, Dibakar.
Thank you so much, Professor, for this warm introduction. Hello, everyone. I will be presenting on my talk, which is titled as Learning Hidden Physics and System Parameter with Deep Operator Network. And this work has been done in collaboration with Bosch, Bangalore office, and my advisor, Professor Somdata Goswami. So this presentation will be divided into two parts, where in the first part, I will be talk about neural operator for system parameter identification. And the second part, I will talk about deep hidden physics operator. And we will go over the motivation of proposing this architectures, proposing this framework, some of our results, and we will conclude with key takeaways. So let's start with the neural operator for system parameter identification. And let's formalize the problem statement that we aim to solve. So given some kind of a PDE, considering a Burger's equation, where we have some primary field, velocity in this case, and we have some parameter, nu, viscosity in this case. And our goal is to recover this unknown viscosity from the sparse measurement of U, which is a typical inverse problem. In order to solve this problem, we do some kind of optimization. Here we have basically aim to minimize the data loss given some constraint of the PDE residual. Now imagine let's say we have a very good optimization framework which converges in 500 iteration. If we have to solve for multiple different scenario of this input-output data pairs, then we have to run this optimization algorithm n number of times given based on our requirement. And thus the computational cost of this whole framework also increases like 500 cross n or something. And thus this problem becomes very computationally expensive. So the solution for this is to build some kind of a parameterized operator learning framework where we have to map an operator which learns the mapping between some sparse data to the viscosity field. And there are a lot of several works on this topic, where I'm particularly showing two paper here, where Molinaro presented some neural operator, inverse operator framework, where they are trying to solve some problem where if you have some Dirichlet to Neumann mapping or sensor to receiver mapping, then they are trying to identify some kind of a material property from the boundary measurements. Moreover, there is a work by Long et al., where they have proposed an invertible Fourier neural operator, where they introduce the invertible blocks to make sure that they are learning the forward and inverse mapping of the input-output pairs simultaneously in one training step. All this parameterized operator learning relies on supervised data, means we need the input-output pair, and that's when we will be able to learn this learn this parameterized operator. However, the question that we are asking in our problem is, what if we don't have this input-output data pair? Can we discover the parameters as well as learn this mapping this parameterized mapped operator, which will help us solve for different problem for different scenarios, and what is the most effective framework for this supervised, unsupervised, or self-supervised parameter discovery task. And thus, we proposed this neural operator for system parameter identification framework, where we have a two-phase training, where in the first phase, we are just trying to learn some kind of a solution operator, which maps from the sensor data to the primary field. And we are learning it with some kind of a sensor data loss. And if you see it carefully, this is basically nothing but just an identity mapping, where we are trying to give some kind of input is the data, and we are just trying to capture the whole data as much as possible. And this initial step give us a very good initial guess of our primary variable, so that we can carry it forward and do some kind of a discovery based on this good initial guess. And thus, we do a continual learning transfer of the learned parameter of our solution operator, and introduce an inverse operator represented as G5, which maps the sensor data to the corresponding parameter, which is represented by nu in this case. And we combine the solution and the parameter with some kind of a PDE loss. And we have this new loss, which consists of some PDE loss and the sensor data loss. And we try to minimize this with some kind of optimization algorithm. Now, the outcome from this training step, where we will get basically two different sets of learned operator. One, which can give us a solution given the input data. Second, which can, given the input data, it can give us what is the parameter of interest. Let me showcase some of our results that we will get from this operator learning framework. So consider a heat equation where we have to determine what is the conductivity field. We're considering an L-shaped domain, and the parameter of generalization in this case are the initial condition. So initial conditions are generated from different Gaussian random field. And we also have different heat conductivity coefficients as well. So we are taking a combination of 100 cross 100 pairs of this initial condition and different heat conduction viscosity. And we are assuming like some kind of trying to make sparse measurements of data. In this case, we have 40 different sensor locations throughout the domain, and we are only collecting 11 times steps, 11 times snapshots, you can say, in between the time domain of 0 to 1. And by looking at the test cases, which is 1,800 different pairs of initial guess and the conductivity, we have seen that if you plot the distribution of the error of the absolute error of the prediction of our heat conductivity, we have seen that it is skewed towards 0, which means that in most of the cases, it was able to predict the conductivity quite accurately. And if I have to show you one representative sample, you can see in the middle, if you run an FEM simulation for this specific problem using K of 0.084, we will have this kind of field or this kind of temperature field. And the predicted coefficient is we get is 0.047, which is like really close to what the accurate result is. And we also have very good accuracy in the field prediction as well from the DeepONet that we have predicted. And we have also tried different equations, but I will show you one of the most difficult problem here, which is the Helmholtz equation, where we aim to reconstruct the source, which from some sparse measurements of the primary field. And in this Helmholtz equation, why this is difficult? Because we have to learn multiple parameters simultaneously. And in order to simplify the problem, of course, we have considered a parameterized source function, in this case, a Gaussian blob. And we are trying to approximate the amplitude of this Gaussian blob or the center of location of this Gaussian blob. And in this particular problem, we saw that if we take a very sparse measurements like 10 cross 10 or 8 cross 8, which is not, it is not enough to actually learn or discover these parameters simultaneously. And that's why we have to take some kind of dense measurements at 32, because 32 is not actually the very dense measurement. This problem was solved in 100 cross 100 uh, discretization in the using finite difference solver. And we have observed that in some 500 test samples, we were able to closely approximate the parameterized the parameterized source. So I'm actually showing you the absolute error of the amplitude and the location of the Gaussian blob. And if I show you some kind of a representative sample from one of these test cases, you will see in the top we have a reasonably good approximation of the primary field, which was expected because of a very high number of data. As well as we have good reconstruction of the source. In this case, you will see is a true source, and we have this reconstruction of the source, uh, which we think is reasonably good approximation given the complexity of the problem. Uh, Now, I will also showcase some of the ablation study, which actually lead us to some interesting uh, findings. For example, if we try to add some noise in the data set, which is basically the real problem in the inverse problem, because in most of the cases we will have some kind of noise in the sensor data. Here I'm showing you all the average absolute error in the parameter as well as in the field variable. If we add or increase the percentage of noise, uh, and you will observe, and we have observed that it have a very stable growth with error. Like if you increase the data noise, there will be an increase in error that is obvious, but the stability in that increasing error is very good, and it is not going very high. And there is only one outlier in this case, which is the Helmholtz equation, and specifically the amplitude parameter in the Helmholtz equation, which is actually very sensitive to the noise. And you will see that since it is affecting the amplitude very heavily, and that's why you will also see some effect in the approximation of the field variable. So it sometimes go up, sometimes go down. But for all the other parameters, it was able to capture, or it was able to handle noise up to 5%. Moreover, if we increase the data or decrease the data, what will happen? So in this plot, I'm showing that we are increasing the sensor locations or number of sensors for each and every problem. And we are trying to see how the results change. And it was expected that if we increase the number of sensors, the approximation of the primary field will be better. You can see in this right plot. Uh, However, there is still an outlier here, which is the Helmholtz equation, which suddenly increases. The reason is the same, is because of the amplitude parameter, which was creating a lot of problem. And one thing to note is that you can see that there is a very good reduction in the error in the field variable. However, in all of the parameter, you will see that there is an increase in the absolute error. And the reasoning behind this is that if we add more, so if you recollect, we have two different loss functions that we are training combinedly. And thus, if we increase the number of data points in the data loss, then the optimization pushes that field to solve it more accurately. And so the question is, does that mean our solution is strong if our absolute parameter is increasing? Well, not in every case. Why? Because all of these problems suffer from non-uniqueness, and they have multiple solutions. So we might have find some solutions which are accurate, but how can we judge them? So in order to judge it, we basically try to extend the current framework to learn all the possible solution given the input parameter. Basically, we are trying to learn the distribution of the parameters given some input data. So we have the same architecture in this case with very small extensions and with minor changes. Similar to the slide that I've shown earlier, we have like a pre-training stage where we are trying to learn some kind of a solution operator, and we carry forward this parameter to go to the next stage, which is the parameter discovery stage. Now, in this case, the inverse operator that we have, instead of producing one parameter at a time, it is giving us a mean and a standard deviation of the parameter, and we are uh, sampling the viscosity using some reparameterization trick, and we are adding a regularization, which is a KL divergence loss, and we are assuming some kind of a prior, and making sure that the posterior that we are approximating is close to this prior, so that the approximation doesn't go wild. Uh, and these actually help us capture the distribution of the parameter or the distribution of the all possible solutions given the input sensor data that we have. And here I will showcase you um, some of our results. And I will go for the slide to help you interpret the results. We have the same problem, which is the heat equation, where we tend to determine what is the heat conductivity coefficient, given some sparse measurement of U. In this case, it is the temperature. And we have taken, from the test case, we have taken two samples or two different data, and we have feed it inside the inverse operator and the inverse operator predicts this two distribution, which is shown in the bottom. Now the green line shows the actual conductivity parameter, and you will see that it is actually lies inside the distribution which is predicted. Now, in order to check whether these distributions are correct or not, we are sampling 5 random conductivity from this distribution. And for each sample conductivity, we are running a numerical simulation, FEM in this case, to compute the responses at the specific sensor location, which are nothing but the predicted value. Now, these numerical simulated results are compared with the sensor data input, which is basically used to predict this distribution. And we have seen that these two values matches in most of the cases, which shows that uh, we can actually go back to the input parameter given these heat conductivity coefficients. And it also shows that, yes, we were able to capture like the combination of solution which can lead us to the input data, which basically was the target of this task. Now, if I should go to the problem where we have multiple parameters to identify, which was the Helmholtz equation. And here I'm showing you a representative sample. And you will see that we have some approximation of distribution for amplitude and the location of the Gaussian block. And if we sample some amplitude and these parameters, then we can also compare with the FEM solution and the input which is used to evaluate the distribution. We will have a very decent match with an R square of 0.98 or 0.99. The reason behind this is because, again, the amplitude parameter, you will see that the true value is actually outside the predicted distribution for the amplitude. And the hypothesis is that the amplitude posterior might be multimodal, or the model is not able to capture the amplitude uncertainty completely. And one other thing to note here is you can see that the standard deviation for these distributions are very small in this case compared to the previous case because of the problem itself. Generally, Helmholtz equation have more uh, unique solution than the heat equation. So you can see this kind of, so model was able to capture this kind of non-uniqueness nature of the problem itself. Now, from here, I would like to move forward to our next framework, which basically is deep hidden physics operator. I would like to give a motivation behind why do we actually care about deep hidden physics operator with some by recollecting the operator learning task in data-driven and physics-informed case. So basically, if we see the deep operator network architecture, which tries to learn some mapping between infinite dimensional function spaces between some input and output field, and it tries to learn this by minimizing some data loss. One of the limitation of this type of problem is what if we have some gap in the data point, or if we see we have only two time steps, we will have a very bad non-physical interpolation in between these data points. And thus, the physics-informed neural operator, in this case, the physics-informed DeepONet was proposed, which basically tells us to add some physics constraint, which will make sure that if we don't have enough data, the solutions space is in the valid physical manifold. Now, the question that we are asking here is, what if we don't have the information of the complete physics and we have the sparse measurement? Then how to solve those type of problem? So this type of problem doesn't, we cannot actually feed it in the data-driven framework as well, or not even the physics-informed framework as well. So that's why we propose a deep hidden physics operator network, which is just an inspiration from the deep hidden physics model by Ricey, where we consider an equation of this form, where the U represents the primary field, F represents some kind of a source term, and N represents a parameterized, not like unknown physics term for the dynamics. And in our framework, in our architecture, we have a DeepONet which takes the source term and the evaluation points and try to predict some kind of a primary variable from this. And we take the primary variable as well as the gradient of the primary variable as an input to our operator. In this case, it's just a simple MLP, and it tries to predict this unknown physics term in a black box manner. And this is learned in one go using this optimization loss, which contains a PDE loss and data-driven loss. And in some cases, if it is given, we can also include the boundary condition loss or the initial condition loss if it is known to us. And we have some interesting findings from this architecture, which I would like to showcase by one specific example, which is a reaction diffusion equation, where we are assuming the term which contains the diffusion and the reaction is unknown. We only have this source, which is the parameter of generalization. Means we are taking different source term from Gaussian random field to evaluate what should be the solution. And when we did some data sparsity analysis, we have seen that if we consider only two time snapshots, time t is equal to 0 and time t is equal to 1, the vanilla DeepONet architecture will completely fail in this case. But our deep hidden physics operator learns it like really well, even without the complete physics knowledge, by only just adding black box parameterized physics. So the key takeaway from this experiment was uh, that the structure really matters a lot if we make sure that the if we are regularizing the solution enough to make sure that this is inside the PD solution manifold, then even without the specific knowledge of the PDE, we will be able to get decently good error, and in this case, which is really good approximation of the primary field. Moreover, we were also looking into whether the learned black box physics was actually a valid physics or not. So what we tried to take this black box model and do a time marching with this model to see is it comparable to the actual reference solution. And we will also simultaneously see the results of the DeepONet that we have learned during this framework. And we have tested it outside the training domain as well. In the, like we are training it from time t is equal to 0 to 1, but we are also extrapolating it into like twice as the time temporal domain. And we have observed that, yes, we don't expect DeepONet to perform really well in extrapolation, but if we use this learned hidden physics, which is black box, and still we can actually get up to twice as the training domain in the extrapolation task mm, in a very considerably good manner. And it also validate that the operator that we have learned, in this case n, is actually learning the actual governing physics, and it's not some random number generator basically. Uh, and moreover, we have also tested some noise simulation studies, and we actually go far to 50% noise. And like, yes, it fails in 50% noise, it's true. But with a decent, if you have 20% noise that you are adding in the data, it have only 13% increase in error. It shows that, yes, even if you have some kind of a noise, the PD constraint is able to act as a very good regularizer to prevent overfitting in the corrupted data. So if I have to summarize the whole talk, so what I have presented. So we develop two operator framework and where we try to learn the solution as well as discover some kind of a hidden physical parameter from sensor data. And this type of parameterized operators will help us reduce the computational cost of iteratively solving for different scenarios. And in both the frameworks, we have uh, provided studies where it shows it is performs good in noisy conditions, as in data sparsity case. And particularly in the deep hidden physics operator, we have shown that if you have only a structure of the PD, and even if we don't know the whole PDEs, we will be able to capture the solution in a very nice way with very limited data. And with that, I'd like to thank you.
Thank you, Dibakar, for the nice talk. Maybe let me open it up for the audience. So if they have any questions, they can raise their hand and I will go to them one by one. I have few questions, but I will go. Let us first open it up for the audience. From the audience, any questions? You can raise your hand using the Teams app, obviously, not physically. Yeah, Rajat, you can go ahead.
Hi Dibakar. The presentation is really good and the work is also really good. I have one question only. In the deep hidden physics network, that the last one where you yeah, the before yeah, here that unknown physics operator, did you do any kind of another analysis, like to try to see, okay, that whether it's learning that properly the physics behavior or not? Suppose like if I raises some like in the case of in this case, like changes the u value or the field value, it affects some like in the case of, suppose if I, not exactly in this equations, there are some multiple equations where temperature and pressures are there. So if I raise temperature, automatically the pressure will got reduced, and all those type of analysis, like whether this black box is learning that behavior or not. Like,
Okay, I'm assuming are you talking about some kind of a coupled phenomena that is happening? If one variable is changed, can it predict can we get the behavior for other variables? Is
yeah,
that the question?
yeah, not exactly kind of that thing. I'm talking about like there are some there is a library called shape parameter optimization. It shape library is there that try to tell, okay, how much that one parameter is affecting another parameter. So you get to know, okay, it is learning the similar behavior which physics is there in the equation, because we don't know, okay, whether that we can see that, okay, on training and test data,
Mhm.
it is performing well, but we don't know how that black box physics
Okay,
operator has learned
I
that
see.
physics, that
Okay.
kind of stuff.
Yeah, okay, thank you for this question. We tested in a different manner. So what we did, so let's say we have this expression of this form, and we say that we don't know this physics, and we are approximating it with some kind of a physics operator. So what we did, we have taken this approximation of n, and we have solved this equation only, which I am showing it in this validation of n slides. Basically, I'm taking this n and doing a time marching, basically. And if I'm learned, like if my physics correct, then I would expect my solution will also be correct if you do a time marching using the physics. And that is how we validate it. And if there is some different fields as well, if that's what you're expecting, temperature, pressure, or any velocity field, then it would, if the physics is learned properly, then we would be able to match all the different field using this learned operator.
Okay. Actually, I was expecting like, is there any quantification, like how that proportional behavior, some kind of stuff that's like, if one thing is going up, that behavior of another parameter will behave appropriately in that same manner. Like, how do I explain? Uh,
It's like
uh,
you want to do some kind of a sensitivity analysis using this operator. That's what you're saying.
yeah,
Like,
kind of like that. Kind of like that. Like,
but
so that I can got to know that
hmm,
that behavior of, because in equation we say that, okay, we can see through equation that it's a directly proportional something, and this
hmm,
behavior is directly proportional to that thing, but we can't judge in the case of unknown physics, like whether it has learned that thing or not. So that's the one, that is the question, uh, uh, because that is the one concern happen when we try to find unknown physics, but we don't know whether it is correct or not, how much it is correct. So that
I
is,
see. Yeah,
so
if you don't
that's,
have the solution itself, that how it is changing, yes, it would be very difficult to judge whether the learned physics is correct or not. But in our problem, we already knew how the solution would evolve,
yeah, yeah,
and we are just testing on that.
okay, okay. Yeah,
Yeah,
yeah, thank you.
thank you.
Yeah, I guess you have to test it on some data that you hold out. You will need some data to test it, right? I mean, whether that
Yes, yes,
matches
it's true.
in the test data. Otherwise,
Yeah,
I mean, you have no
these are all test cases.
way of validating what you're learning is correct or not. I mean, the end part, because that's a neural network in your case. So how do you know neural network has learned do to you, do x2, and it's not possible, right? So I think that was the question. Anyways, yeah, any other question from the audience? Otherwise, I will go forward with my questions. Okay, let me start, and then if others have questions in between, they can raise their hand. I'll come back to them. So in the first part, right? where you are solving the both the problems, right? The forward and inverse problem, or rather the parameter estimation problem. One thing that I missed was what is the dimensionality of the field of the variable? In most cases, it is either 1 or 3. But in a real problem, let's say the Darcy flow problem, the permeability field is the parameter, and it will be a random field, and the intrinsic dimensionality, which is maybe in 1,000. I mean, it's often in 1,000 actually. It need not be smooth that you can parameterize it with 3 parameters or even 10 parameters. So did you check in that case, like high dimensional inverse problem, as we call it,
Yes.
how it performs?
So I tried to solve the exact Darcy's problem earlier, but I did not try to solve it in the case of operators. I was trying to solve for one scenario. And if you don't know, so there are a lot of challenges there. So if you don't know anything about the interior or the subsurface, then we also have to identify where is the interface. And if there is a very big jump in the field, then we also have to make sure that our approximations are able to handle this jump. You might have to do some domain decomposition. So that needs a very careful attention and different type of scheme to actually discover what are these very highly fluctuating discontinuous functions. We have to come up with some like a adaptive domain decomposition scheme, which can make sure that it can learn this kind of permeability.
It can be simpler than that, right? You can assume it to be Gaussian random field, but take the length scale so small that the dimensionality, actual dimensionality is in 1,000. So it's continuous, but because your length scale is so small, the intrinsic dimensionality has increased, and it is now in over 1,000. I mean, there are data sets like that available. I mean, the jump is a real problem. I mean, I'm not even going there. Even the channelized flow, I will say, is a real problem because it switches from 0 to 1. But assume a Gaussian random field, because that I guess that is something you can handle. But now the length scale is so small, you can always tune the length scale, right, for generating your data, such that the intrinsic dimensionality is 1,000 or over that, and you can easily check that using, let's say, the KL expansion, the intrinsic dimensionality for Gaussian random field at least. So maybe that is something, I'm not sure you have checked it or not, but I think that's something worth checking, because that will strengthen or at least give you idea about the strength, right, of your framework.
Thank you. I think that's a really good comment. Yeah, we can actually check on very low.
That is very easy for you to check.
Yeah.
You know Gaussian random field. You can easily check it, right? Anyway, the other part is, you call the first framework, right? This one, unsupervised.
Now, it's actually self-supervised. Yeah.
I mean, will you call physics informed supervised or unsupervised? Forget about this thing. Just physics informed neural network.
I will call it as
the same thing, right?
Yeah. I will call it as a semi-supervised, because I will call this problem of discovering the parameter as a semi-supervised task instead of an unsupervised. Maybe unsupervised was not the correct, because we are actually trying to add some kind of a constraints, the known constraints in our loss function. So maybe, and it is trying to discover the parameters on its own. We are not explicitly saying that, okay, this is the parameter, let's go to that.
Yeah. The parameter part I'm not going, but only because of the pin part, right? So the way I see it again. So supervised is unit level data, right?
Yeah. Yes.
Now in physics informed, it is actually level data. The residual is 0 for all collocation point. In your case, for wherever, right? So your label for each of them is 0, 0, 0, 0, 0, 0, 0.
But we also
that's
have
the residual, right?
But we also have a data.
The data is boundary, right? Yeah, data. The data part is okay, but it's a level data. I'm trying to say, not this one, not your framework. The classical pin or the PINO, that one I'm talking
I
about.
see. I see. Yes.
It's just the forward problem, right? In that case, you can imagine that it's actually labeled,
Mhm.
but the label is 0 for each of those. And you don't have to imagine that's the case because residual is 0. So it's all pair, right? Input is x, comma 0, x1, comma 0, x2, comma 0, and something like that. Now, if I try to look at from, it's a philosophical discussion. If I start to look at from that lens, it becomes supervised. But then you can always say, okay, I don't have U and U is my field of interest. So then it's unsupervised. So you can always have that philosophical discussion, but what is your take on that? I mean, that is what my actual question is. And it's a philosophical discussion. That's fine.
Well, now that you are saying that, it is allowing me to think that it's like you can say that it is actually supervised, but I still feel that since it is like a multiple objective functions are combined together, and we can have multiple solutions of U, and there is no unique solution in the Prince problem. I feel that it is still an self-supervised, so it is like searching for answer instead of telling what is the right answer.
Okay. Yeah. As I said, that's a field discussion. So we can always have that debate on that. And that's fine. It's good to have debates. Now to understand, right? I mean, what is the role of this pre-training part? I mean, it's like autoencoder, right? You're taking the thing and reconstructing it.
Yeah. So basically,
yeah.
yeah. So the idea was, so if we directly solve this problem using this loss function, we will see that this U is also unknown and this nu is also unknown in this case. So there can be multiple U and new combination which can lead the PD residual to be 0. And if the sensor data is not good enough or not dense enough, we cannot actually capture the solution of U nicely. That's why in this type of problem, we have to initialize the solution in a way so that we have a decently good enough approximation of U, and then we are passing that U as an initial guess for this discovery stage. So that was the key idea to actually split this process into phase 1 and phase 2.
But how will you initialize it? Because that sensor data is the data you have, right? And based on that, you are doing the autoencoder. So basically trying to learn an identity operator, right? So can't I directly use the input data, the sensor data that I have, U data, instead of U? What will happen in that case? Or is it like you have sparse sensors and you are trying to reconstruct a full field? Something like that is happening here? No.
Yeah, so basically,
Yes.
yes. So if you see the U data, I'm presenting it as some kind of a very specific 4 lines, means may have 4 sensors. But if we do a DeepONet in that case, we can actually evaluate at any evaluation points. That's why basically we are trying to reconstruct the whole field. Yeah, in this case,
Got it.
and it can
Got it.
Yeah.
So it's more like a state estimation kind of problem that you have some points, but because there is a DeepONet sitting, yes, the loss function is like you have to get an identity, but once it is there, the prediction is not restricted by those sensor location. It's a full field.
Yes.
And that full field is used for initialization, right?
Yes.
Okay, got it. Yeah, this part was not clear for me. Okay. Yeah. Next is because it's in a operator setting kind of setup. So how does it perform something like out of distribution data? I mean, right? But let's say you trained it for that, but now I have something from a different distribution.
Oh, okay. So
Was
the out of distribution. Yeah, I think I got the question. So the question was regarding out of distribution testing. Well, we did not really test on an out of distribution sample. We considered a very specific Gaussian length scale and Gaussian GRF parameters, and they are tested and splitting on that. I don't consider it as out of distribution, but my take is it might not be able to handle it very nicely, but there is a chance that it it might, because of the PD residual, if it is constraining well enough, it might able to handle. But that's still a question to answer.
Okay. Okay. Coming to the uncertainty part, which is naturally of interest to me. So you have you are taking the mean and SD, right? And it is capturing the PDF or giving a PDF, which is the uncertainty. Now, I was wondering, and that what uncertainty is it capturing? Because if you think about uncertainty, there can be uncertainty because your sensor data is sparse.
Mhm.
There can be uncertainty because your sensor measurements are noisy.
Mhm.
So limited data can be there, and limited data can be there, and noise data can be there. And along with that, there can be because of model discrepancy, that your model is not perfect.
Mhm.
Now, those model discrepancies generally come in physics-based model because you make some assumptions and approximations. And when you do Bayesian, and that is the beauty of Bayesian, you can put finite one portion of the noise, the uncertainty. If you have zero noise, the other part of the uncertainty will go to zero. And if you have infinite data, no noise, the uncertainty will be at zero, so you will get a direct delta guiding, which is a mean prediction, right? Mean direct delta spike at mean. Now with this, which uncertainty are you capturing? I mean, can you assign some physical meaning to the uncertainty that is being captured in some meaningful way? Or is it just acting as a regularization? Because that's also a possibility, and that's why you are getting better results. But uncertainty do not have any physical meaning. So your comments on that? Any comment?
Yeah, like when I thought of this, I was just considering like it might act as some kind of a epistemic uncertainty where we don't know the right value, but yeah, that's when you are defining this model uncertainty, sparse uncertainty. Uh, uh, I haven't really thought about what specific uncertainty it is estimating, uh, because it is like it's trying to capture all of them, but I think it is just trying to act as a, like just how the last point that you mentioned, maybe just as a regularizer, which is making sure that it is able to capture
Training
a good
is
and a good, yeah, good
training
and
is good,
solution.
right?
Yeah,
Because if it is epistemic, then you should be able to reduce it, because epistemic uncertainty is
yeah,
also known as reducible uncertainty. So by
reduce
the
it.
correcting, you can reduce it,
Yeah,
right? But
so
in this case, I
if
doubt
so,
you can reduce that sigma b. So
yeah, that
it's
is also true.
more, I don't know, I'm not very sure. But maybe, yeah. Maybe the regularizer, maybe we do not know. That's also can be a
Mm.
thing. Uh, yeah. Lastly, regarding the second part, right, which is the hidden physics part. So if I understand correctly, what you are doing is that you are assuming that my model is dy by dt is equal to f of y. And let's assume more than that f of y as a neural network, right?
Yes, true.
Or neural operator in your case.
Mhm.
So is it not very similar to node, which is the neural ODE or neural PD, whatever you call it, depending on the equation? That is one part of the question. The second part of the question is kind of obvious, I think, but I mean, the inference time is compromised here. You are probably getting very good accuracy with this, but the inference time is much more. You have to use a numerical simulator now. During or time much because of a differential equation. And I think that is something you showed in the next slide, I think also. So yeah, this two-part question, which is my last question also.
Uh, yeah, okay. I will like to, okay. I will answer the first question, and the second question I didn't get it because of the network. Maybe I will just answer the first question first.
Yeah, I'll repeat. Just answer the first question, I'll repeat the second question. Yeah, there is some
Yeah,
network
so
inside.
so yes, you can actually definitely see it as a like a node. Uh, but I would argue that like node do it in a very different way because you have this label data of like the next time step data, right? And you try to learn
Training is different.
this. Yeah, training is
Training is
different.
completely
And
different.
yeah,
You have
so
differential physics and all those things. Yours is physics informed node, I'll call it. I mean, if there is
yeah,
something like that.
yes,
In
and
some sense, the training is different, but the model looks like node. Or
yes,
rather, I should say, generalization of node with operators. I mean, even I'll say generalization of node with operator. Node is a generic network. It need not be operator, right? In your case, I
yes,
guess N is a DeepONet.
yes. So actually, in this case, N is just an MLP. You can actually
Oh, okay.
say it as like a operator framework for a deep hidden model, the deep hidden physics model. So deep hidden physics must also do the same thing. So and we are just doing it in an operator case.
Okay, okay. Yeah. And I think your hyperparameter choice is what derivatives you will keep as input for the N. UX, UXX, that is a choice you will have to make, right?
Yes, that's a critical choice actually. We can go
Obviously.
and it increases the input space a lot. So we have to choose it very wisely.
And this UX, UXX, you are calculating using automatic differentiation, if I'm not wrong.
Yes, because we already have this U. So we are evaluating
Yes.
an automatic differentiation.
Yeah. And the second part was that because of this node kind of structure, right?
Mhm.
My guess is that it will be expensive. You've written here also UHPM, and it will be expensive because you have to use some time matching scheme, and time matching size. So you are getting this efficiency, or it's a trade-off, right? As always is with
Yes,
coding.
yeah. That is always a question when we have
So
to
is
deliver
that
some model.
understanding correct?
Yes, you're absolutely correct. But like the main goal was is to see how we can use the physics. And yes, if we are doing a time
Yeah.
matching scheme, we can get good results and it will be expensive. But moreover, our point that we wanted to make is that like if we have this kind of a structure, then we can actually get the solution with very, very less data. And in this case, only 2 time steps. So that was the point of
Yeah.
interest that we want to convey, that we might not even need the complete knowledge.
Yeah. There is no doubt about that.
Mm.
There is no doubt about that. And yeah, sorry, from your answer, another question came to my mind that what about so did you try different time step during inference? And how much does it affect your final prediction?
Oh no, we go with a very simple Euler scheme and fixed time step. We didn't try different time steps actually.
Yeah, when I say different, I mean Euler scheme, but let's say you are using
Uh-huh.
0.01, 0.001,
Yeah, yeah.
0.00001, and how much does it affect during
Yeah, that
inference?
we did not actually test it on different
Okay,
time steps.
okay,
Yeah, we kept it fixed.
okay, okay, okay. For the last time, let me ask if there is any other question from the audience. I asked many questions because it was quite interesting. And when a talk is interesting, there are many questions, right?
Thank you
So,
so much
yeah.
for all the questions.
Any questions from the audience? If not, I don't see any hand raised. Maybe we can let me thank Dibakar once more for this nice presentation. And thank you everyone for joining in. And yeah, we'll meet once more next week before you go on the vacation and come back in next year. Thank you and
Yeah,
have
thank
a
you so
nice day.
much. Yeah, thank you.